Let's take a look at a type of polar graph called a one-loop limaçon. A one-loop limaçon has two different forms that we can graph. The first form is r equals a plus or minus b sine theta, and the second form is r equals a plus or minus b cosine theta. We also have some conditions for a and b. Both a and b must be positive numbers, and the ratio between a and b must be between 1 and 2. This means that a must be greater than b, but less than 2 times b. Although we have two forms, we technically have four equations for limaçons. First, we have the equation r equals a plus b sine theta. This equation gives us this graph. Next, we have the equation r equals a minus b sine theta, which gives us this graph. Notice that the second graph looks similar to the first. By replacing the plus sign with a minus sign in the equation, the graph of the limaçon gets reflected across the polar axis. Notice that both of these graphs are symmetric about the vertical line theta equals pi over 2. Our next equation is r equals a plus b cosine theta, which gives us this graph. Finally, we have r equals a minus b cosine theta, and with this equation, the graph looks like this. Again, notice that by changing from addition to subtraction, we get a reflection of the graph. This time, the graph is reflected across the vertical line theta equals pi over 2. With the cosine function, the graphs are symmetric about the polar axis. We can use these equations and their graphs to get a general idea of what the equation of a limaçon will look like on a polar graph. Now let's look at another type of limaçon, called a two-loop limaçon. Two-loop limaçons also have two forms that we can graph. You'll notice the equations themselves are the same as the ones we use for one-loop limaçons. The difference is in the way we define a and b. Here we have that a and b are both greater than 0, but a must be less than b. Again, we have four equations that will give us the graph of a two-loop limaçon. The first equation we'll look at is r equals a plus b sine theta. This equation gives us this graph. If we change the operation from addition to subtraction, we get the equation r equals a minus b sine theta. The graph of this equation looks like this. Notice that the graphs are reflections of each other over the horizontal polar axis and that they are both symmetric about the vertical line theta equals pi over 2. The third equation is r equals a plus b cosine theta, which gives us this graph. Notice that the graph changes to a horizontal orientation when we use cosine instead of sine. For our last equation, we will again change the operation to subtraction, which gives us r equals a minus b cosine theta. The graph of this equation looks like this. Again, notice that changing the operation reflects the graph, this time over the vertical line theta equals pi over 2. Also notice the symmetry here. With the cosine function, these graphs are symmetric about the polar axis. We can use these graphs to establish an idea of the graph of an equation for a two-loop limaçon. We want to graph this equation of a limaçon. First, we'll need to determine if we have a one- or two-loop limaçon. We know the equations for limaçons are of the form a plus or minus b cosine or sine theta. So, in this case, we have a equals 3 and b equals 2. This equation uses cosine. Since a is greater than b, but less than 2 times b, we know the ratio between a and b will be between 1 and 2. Therefore, this is a one-loop limaçon. Now we can go through the process of graphing the equation. We first want to test for symmetry. We saw before that a limaçon is symmetric about either the polar axis or the vertical line pi over 2. An equation is symmetric about the polar axis if we can replace theta with negative theta and have an equation that is equivalent to the original. So we'll write r equals 3 minus 2 times the cosine of negative theta. Recall that cosine is an even function. This means that the cosine of negative theta is equal to the cosine of theta. Since the two are equal, it doesn't matter which we use because the outcome will be the same. This means the equation passes the test for symmetry about the polar axis. Next, we want to find the zeros of the equation. To do this, we will set r equal to 0 and solve for theta. However, this results in theta being undefined. Recall that the angle theta is undefined for any value of cosine theta that is greater than 1 or less than -1. What this means for us is that the graph will not pass through the pole. However, it may pass through the polar axis. We can determine whether or not this is true by finding r when theta equals 0. The cosine of 0 is 1, so we are left with r equals 3 minus 2 times 1, which simplifies to r equals 1. So we know there is at least one polar axis at intercept 1, 0. Next, we'll need to find the maximum of r. Consider where the maximum of the cosine function occurs. Notice that the coefficient of cosine here is -1. This means the value of cosine will be greatest at -1. Solving for theta, we get that the cosine of theta will equal -1 when theta equals pi plus 2k pi, where k is an integer. So we'll solve for r when theta equals pi. This gives us r equals 3 minus 2 times -1, which simplifies to r equals 5. So our maximum value occurs at the point 5 pi. We'll need to find more in order to graph the limaçon. Let's create a table and use values from 0 to pi in increments of pi over 4. We already know that r is equal to 1 when theta equals 0, so we can write 1 in the first row. Next, evaluate the function for pi over 4. The cosine at pi over 4 is roughly 0.71, so we'll multiply this by 2 and then subtract the result from 3. This gives us 1.58. When theta equals pi over 2, the cosine of theta is 0. This gives us 3 minus 0, which is just 3. Now we'll evaluate the function at 3 pi over 4. The cosine of theta at this angle is -0.71. As with our second calculation, we'll multiply this by 2 and subtract the result from 3. This gives us a value of 4.41. Finally, we'll need our maximum value. This will give us a value of 5. Now that we have a set of points to plot, we can plot the limaçon on a polar graph. We can see each of these points plotted on the graph. Recall that our test for symmetry told us that the graph of this limaçon is symmetric about the horizontal polar axis. Therefore, if we mimic these points, we are able to draw the full shape of the limaçon.